Now start basis for a topology and remaining part after lemma and example. Previously we see that tau dash, that means is finer than tau, that means we compare two topology tau and tau dash on a set, and these two topology represent two basis element script beta and two basis script beta and script beta dash, and then if anyone finer, then their basis element is subset of another one. Now we start about some definition. Some beta dash is the collection of all open intervals of in real line. That means beta dash the collection of all open intervals in A. How this one is? See, we know that AB equal to X such that A less than X less than B. Okay. In this way, we represent the collection of all open intervals in our script beta, and this script beta generate general topology. Generate a topology. We call it standard topology. Next we think about another collection of sets or half open intervals of R. This one we denote beta dash. Beta dash is the collection of half open intervals, of the form closed A open B, where this represent by X such that A less than equal to X less than B. This represent this script beta dash to generate some topology. Generated a topology whose topology is called lower limit topology. And it denoted by RL. Next we see that beta double dash is the collection of all open intervals open AB along with the sets of the from AB difference K. That means beta dash the collection of all open intervals AB along with the sets of the from AB difference K, where K equal to 1 by n such that n belongs to Z plus. Then this beta double dash generate a topology we call it a K topology. Okay, then three definition of topology from basis element we now study. Now we compare with both. That means we draw some lemma. This lemma represents this lower limit topology is, and the lower limit topology and the K topology is, lower limit topology and K topology is finer than the standard topology. Okay, and also lower limit topology and K topology are not comparable. This one is a simple lemma. We prove it. How we prove it? Proof. Just draw the sketch. Tau dash, tau double dash. Tau be a topology, tau dash topology and tau double dash topology of R. Here RL, here RK. Then we know that here basis element in the from this one. Here basis element of the from XB where A less than X, and here basis element are in this from AB minus K, where K equal to 1 by N such that N belongs to Z plus. Okay, then we see that we construct a basis element here. Obviously this element contained in AB, and any point X belongs to this one is done. That means tau dash is finer than tau. Obviously from here X belongs to AB difference K subset of open AB. This implies tau double dash is finer than tau. Okay, but we see that what we see that these two intervals will not compare with each other. That means if any element y, here we take any element y or z, anything. Okay, not x because x is taken here. Okay, y, any element z belongs to this xb. This does not subset of AB minus K, and also we can take P belongs to AB minus K. This does not subset of XB. So we call, from this assumption we called RL and RK are not comparable. This one is very simple. We see that RA lower limit topology, RK lower K topology, R standard topology. Then RL is finer than R and RK is finer than R, obviously strictly finer than, but RK and RL are not comparable. We see it better. Now further proceed the definition of subbasis. One important topic, subbasis. We know about now basis and some lemmas of basis. Some important properties shows this lemmas. Now we proceed to subbasis. Subbasis for topology on X. Subbasis, we write the definition. A subbasis is for a topology on X. For a topology on X is a collection of subsets. Is a collection of subsets of X. Subsets of X is a collection of subsets of X whose union equals X. Whose union equal X. Also, the topology generated by subbasis is defined to be the collection tau of all union of finite intersection of element of S. That means if beta 1 some basis element, then S1 intersection S2 dot 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 Sm finite intersection of subbasis element represent this basis, and obviously if beta 2, then S1 intersection S2 intersection Sn finite intersection of subbasis element, then obviously beta 1 intersection beta 2 must be this one. This one if denoted by dash, then S1 dash intersection S2 dash Sn dash is a finite intersection of S, so it belongs to B. That means it also belongs to B basis element. That means B some basis element, beta 2 B2 some basis, B1 B2 some basis element, then also B1 intersection B2 is a basis element. Now a topology generated by subbasis S is means the collection tau of all union of finite intersection of elements of S. Finite intersection of elements of S, union of all finite intersection of elements of S represent the topology. That means topology tau equal to, then topology tau equal to S1 intersection of Sm union S1 dash intersection of Sn dash. In this way, if more basis element is here and we represent by this finite intersection of subbasis element, then topology is the union of finite intersection of subbasis element. Okay, here some definition of subbasis. Subbasis for topology on X is a collection of subsets of X whose union equal X. That means subbasis represent finite intersection of some subbasis element. Finite intersection of some subbasis element. Now we interesting two topics. One is intersection of arbitrary topologies is a topology, but union of arbitrary topology is not topology. We know that topology, if tau alpha is be a topology where alpha belongs to index set, then intersection of tau alpha belongs to index set, be a topology? Because all these properties of tau alpha belongs to this intersection of tau alpha. Okay, but union of tau alpha be not a topology, not a topology. How we represent it? Tau 1 equal to phi x singleton 1 and tau 2 equal to phi x singleton 2, then phi x equal to 1 2 3, then tau 1 union tau 2 equal to phi x 1 2. This be not a topology, not a topology. Why this one is not a topology? Because 1 union 2 equal to 1 2 does not belongs to tau 1 union tau 2. Now we proceed further. This one is the largest topology and smallest topology from two topology. How it can be obtained? We see it. Two topologies here. Tau 1 equal to phi x singleton a singleton ab, and tau 2 b phi x singleton a singleton b and bc. So tau 1 and tau 2, if tau 1 and tau 2 contain, that means tau 1 and tau 2 contain some smallest topology, this one contain tau 1 and tau 2, that means tau phi x singleton a singleton ab singleton bc must contain in it. And now one singleton b added, because these two intersection ab intersection abc must be b belongs to this topology. So this one is the smallest topology, which contain tau 1 and tau 2, and also the tau equal to and tau star equal to phi x a b c a b a c b c be the largest topology, which contain tau 1 and tau 2, So we end the topics basis for a topology.